All right, so now let's talk about O of n squared algorithms, or quadratic time algorithms. So these are algorithms where the growth rate is relatively bad to the other ones that we've had. But they're not like the worst in the world like factorial or exponential time algorithms, as we'll see later. But of the three that we're studying now, they're the worst. And ideally, you want to try to get your runtime below this if possible. So quadratic time means that basically a doubling of the time, doubling of the size that you have, will quadruple the amount of time you have to spend. Or more dramatically, if you have 10 times as many items, we now will take 100 times as long to solve this problem. Let's go ahead and take a look at a very basic one, and you'll see this nested for loop relationship kind of pan out here. So public static public static Boolean, got to have a return type, right? All unique Boolean, list of, again, I'm going to be explicit and say it's an array list of E. List. And again, I have to specify, right now it is looking for a class called E and giving me a error because it can't find one. It thinks I'm looking for I'm specifying I want a list of E's, where E is some class that I have written. It is not. I want E to be a generic symbol, so I put E over here to say E in this function, E, and this function only, E stands as a generic. So here, what all unique will do is that we're going to check to make sure that all the items in this list are unique. I'm going to go ahead and return true over here because I'm going to assume everything is unique until proven otherwise, and now I'll give an example. So if my input is as follows, 1, 2, 3, 4, 5, 6, all the items in this are unique, so I'm going to return true. However, if I do the following 1, 2, 3, 2, 4, 2, 5, right, there's a bunch of 2's in there, so not all the items aren't unique, so that's going to return false. Similarly, if I just simply have like 1, 2, 9, 4, 2, 4, you have 2 2's in here, so it's false. All the items have to be different. And we want this to work for any type, which is why we're doing it as an array list of E's. We don't assume that it's an array list of integers or array list of strings or whatever. Fortunately, we have the dot equals for every single method, so that's nice. So for int I, so now what we're going to do over here is that we're going to assume that everything is unique. We're going to assume we're in this case until we find a single pair of items that isn't unique. And once we find that case, we will be able to we can just stop because we found a pair that isn't unique. We disqualify this assumption. All right. So what we'll do is that we will say for all the items, list.size. So for every item in this list, first, I'm just going to call this first item is equal to list.getI. So right now, as we're working with this list, this for loop does n operations. And this operation over here is constant time. So we have n constant time operations. So we are O of n as it is written right now. But all we're doing is retrieving an item called first item. What we have to do to check if all the items are unique is compare each item to every other item. Each item has to be compared to each other item. So we've got our first item, but now we have to check it against all the other items. So we need an additional for loop. There's just no way around that with the current restrictions we currently have. I'll show you in a bit a way we can do it faster using a data structure we'll learn later. So for int j is equal to 0, j is less than list.size, right? And we're going to do this a couple of different ways to refine it, because there's a lot that's going to be over here, including a bit that's relevant for your homework. So for int j is equal to 0, j is less than list.size, j++. So here we're going to say e second item. And be sure you're using j over here. It's a very common mistake to accidentally hit I in an inner loop. List.get j. See, like I just did over there. So first item, list.get I. Here we're going to go through all the other items. And here we're going to go through the list again and get all the items. What I will do over here, though, is put in a specific statement. If I equals j. So if the two indices are equal to each other, then I'm just going to put this in. Continue. So bit over here. What this loop says is that basically if the index for I and j, if the first item and the second item are the exact same location, right? Not this, we're checking the same item, but we're checking if we are hit the same exact location, then in that case, I would get a false positive because every item is equal to itself. So to avoid that, I do this, I put in this continue statement, which just simply says, move on to the next step of the loop I'm in. So this just means, just stop this and go on to the next j. So e item, so we get the second item, and now we just simply say if first item dot equals second item, return false. All right, so now let's take a look. Again, we're going to do a worst case scenario analysis here, which is that we are going to assume that actually, worst case scenario, they're all unique. Why is this worst case? Because this means we'll have to check every single pair. So we get our item, and then for each item that we grab, we look through all the other items, and then we compare it. So this takes O of n time. This operation inside of here also we know takes, that takes constant time, and this operation also takes constant time. Checking if two items are equal, also constant time, right? And checking to see if these two things are equal, also constant time. But this loop goes through the entire array, meaning it's O of n. Okay, technically we will, it means it's O of n. You have to do a check over here, for I is equal to j, but we can kind of ignore that because it's just an outlier. So here, we've got, let me go ahead and just put n here. So this outer loop runs n times, and each time it runs, it performs this constant grab, as well as a for loop that runs n times. So n times n, right? This for loop runs n times, and inside of it is a for loop that runs n times, right? So each loop of the for loop will have an operation that performs n times. So n times n squared. This is a quadratic relationship. So let's go ahead and test it out. Right, so all unique. Let's go ahead and test it out on 100 items. Notice I'm starting small. True, they're all unique because I've just added them all. Let's go ahead and do then list.add 0. Right, at the very end. Should give us false. Also, but it's first item and second item, but the first item and the last item are the same, so that's not a worst case scenario, but it's fine. But we've proven that this works, so I'm just going to again run it like this. True. Now let's bump it up to 100. It's already 1,000. So 13 milliseconds. Now let's bump it up to 10,000. 135. And now, once I bumped it up to 100,000, I could actually cut away here and come back. I just don't know how long I'd be waiting. Oh, there we go. So that was 12,609, right? So we finally got to a point where basically it's a noticeable difference. So notice that it took 100 times longer to do 100,000 versus 10,000. The other ones were just, we weren't getting that 100 times growth because they were still just so small that their computer could go through them really quickly. But you don't even need to bother slowing it down. This took 1/10 of a second. Doing this took about 10 seconds. If I did this, this would take, let's see, well, what's 10 times 100? That would take 1,000 seconds. That would be quite a long video. So this operation takes a while, right? Let's go ahead and go back, right? This is 10,000, took 137. So let's double it, right? That should be 4 times as long, right? We went from about 140 to about 4 times as long. Okay, there's gonna be some jitter. That's okay, right? The idea here is that it approximates this quadratic curve. Let's go ahead and go to paint again. So the curve we're looking at is something like this, or just straight up this kind of curve that we're looking at. All right. Now, you might think to yourself, well, wait a second. We could write this smarter, couldn't we? We could, we're checking every item against every other item, right? I check once against 2, 2 against 3. I check 1 against 2, 3, 4, 5, 6. But then I check 2 against 1, 3, 2, 4, 5, 6. And then 5, I'll check against 1, 2, 3, 4, and 6. But by the time I've got to 5, I will have already checked 1 against 5, 2 against 5, 3 against 5, 4 against 5, right? I'm repeating a check that, just with what's the first item and the second item flipped around. And if they're equal, it doesn't matter what order they put them in. And I'm going to go, okay, I'll give that to you. So let's go ahead and change that, right? And I'm going to go ahead and rewrite this actually. So for each item in the list, right? For each loops look so nice. Then what we'll actually no, I can't do that. I can do it for the first time because we need the index here. So now what I'll do is I'll say j is equal to I plus 1, and so long as j is less than the size, yeah, so long as it's less than size, we'll do that. So we're only going to now check the items to the right of what I'm at. So, and if, and so now we can just simply actually simplify this, make it a bit easier to read. If list.get I dot equals list.get j, and so easier to read for some value of easier. Right. So if the item at I is equal to the item at j, again, this inner statement over here, this if statement runs once. So each pass of the loop will run approximately n times, but it's not quite, right? It should be shorter because the first time it will run 5 times, then it'll run 4 times, they'll run 3 times, then 2, and then this guy won't have to check anybody to right of him at all. So, so we're shrinking the number of comparisons. That should make a huge difference, right? So let's go ahead and do 10,000, right? Because we're basically having the number of items we're checking. So 88 over here. Again, 86, 87, right? But if we double the time, it takes about 4 times as long. If I were to quadruple the time from 87-ish to this, we will take, sorry, that's, multiplied by 10 though, takes a lot longer, right? 100 times as long, right? It's still this, yes, it was quicker, but the relationship, this quadratic relationship, still maintained. How is this a quadratic relationship still, though, right? That's not n, is it? Well, here's what we did, right? Let me draw this out. I find that drawing this actually ends up being a bit more illuminative for our students. So suppose we're checking basically n items against n other items, right? For the last item, we'll just be checking, there's basically just one thing to do, right? Which is just simply skip. Let's see. Well, for the last item, we don't have to do anything. For the next item, we're going to go ahead and do one check, right? Check 5 against 6. Then for 4, we'll check it against 4 and 5. Sorry, for 4, we'll check it against 5 and 6. For 3, we're going to check it against 4, 5, 6. For 2, we're going to check it against 3, 4, 5, 6. And for 1, we're going to check it against 2, 3, 4, 5, 6. Right? And so on and so forth. Right? And then as it gets bigger, we will just this will just simply continue until we've got n stars. Right? So we'll have n minus 1 over here, and the last row will have n. But notice that basically that this is drawing kind of a triangle over here. Equation-wise, this ends up being looking something like this. If we assume that, if we go ahead and just add, and just simply assume that basically that 1 will have to do 6 checks, and then 6 will have to do 1 check over here. Just simply bear with me because this will make the math easier. So it doesn't really change anything at all. Then we have 1 operation plus 2 operation plus 3 plus 4 plus 5 plus 6. And if you've done calculus, you should know that this is basically a very classical summation. So if I put it up on Google, right over here, this is the infinite series of natural numbers. If we go up to some n, then basically we can see that this forms the equation of n times n plus 1 over 2. That's kind of a bit more than half of a square, actually, if you think about it. Right? This is a triangle over here, which is a bit more than half of a square, which I can draw thanks to the wonders of monospace fonts. Right? So this makes up a bit more than half a square. Whereas earlier we were doing something like this, right? Everything ran the same number of times. Everything ran the same number of times. Each iteration through ran the same number of times. But here, with the way we've optimized it, we're all only checking the items to the right of us. So 6 only has to check 1 item, essentially. Again, I'm just increasing it by 1 to make the visualization easier. 5 checked. 5 and 6 were 2 items. 4, 5, 6 was 3. 3, 2, 4, 5, 6 was 4, and so on and so forth. Right? Again, it's just making the math easier, which is 1 plus 2 plus 3 plus 4 plus 5 plus 6. And what this is saying is that 1 plus 2 plus... And if you've taken Calculus 2, you'll learn that basically that this equation over here, that is equal to n, that comes down to n times n plus 1 divided by 2. Which, if we multiply this out, by the way, this becomes what? It becomes n squared times n over 2. And now, when we do big O analysis like this, or sorry, n squared, not n squared times n plus n. Now, when we do, this is a great example of big O, of how we handle big O stuff. So first off, when we compare stuff to, when we take some amount of time that something's going to take, how many operations this is going to take. Say it's t of n squared plus n over 2. How do we turn this into a big O, right? I've just kind of been eyeballing it so far. But how do I turn it into a big O? Well, then I get something more complicated like this. Well, for big O notation, again, all we care about is the growth rate. So we just simply do 2 things. First, remove all constants. Constants and coefficients. So we're going to remove the 1/2 because that's a coefficient. Don't care if it's half of n squared, whatever. Just remove that because it's not going to matter once n gets to a huge size. That doesn't affect the growth rate. It just simply affects kind of the starting point for it. the next thing we do is n squared plus n. We just simply always take the largest degree. N squared is much greater than n. And to figure out which one is going to be greater, just simply like bump them up to some huge number, like a million or a million to the millionth power. And at some point, this n will become inconsequential. It will become some error, rounding error. So we just simply drop the lowest figure. Again, this will be in the first page of your practice. And if you need more details on this and the more formal write-up on this stuff, your book has this. Right now, I'm just trying to give you a feel for these algorithms so that we can simply look at, when we go over our data structures, it'll be much easier. So we can simply say this is O of n squared. So the last thing I mentioned, and I know this video is going to get hideously long, so I think I'm going to have to trim this down, and I'm going to have to do this next part as a separate video.